know each other for a while now, but my first time here in Valparaiso, Santiago, Chile before. So with that, I'd like to, I have to admit I had some difficulty in preparing the presentation, simply because I didn't know what I should cover and what I should leave out, what would be of interest in this group. But nevertheless, now it's too late to change anything. And okay, the other thing is, after David said a very good joke yesterday, and Gers said another good joke last night, I couldn't find one. So, that's a good joke. Or at least one that I could tell quite obvious. Anyway. So instead, I picked some pictures here. That's not a joke, but since also there will be students in the audience, I'm at Northwestern, as we saw in the first slide, and this is how Northwestern looks, not right now, in a different season. And somewhere there is my office, so we're next to Lake Michigan, and there's a campus downtown, and one at 11, so you go sailing in New Zealand. But of course, it's not just for fun. Everybody's invited to maybe come visit or apply there. They're also doing some work. And as far as my work goes, I've been directing this lab here since '85 that I joined Northwestern quite some time ago. That's when I got my PhD as well. Quite a few people graduated under my supervision, and in my lab there are about 20 to 25 people at any given time, depending how you count. And we're doing work in the intersection of different areas. I come from the signal processing, image processing area, then computational imaging, you try to touch the acquisition system, some communications, and also late in the last 10 years also machine learning. This is the book we published 2016. There's a second edition coming out next month, and also the tercera course there, just some advertisement. Okay, so what I'd like to talk today is about some inverse problems in computational imaging. And I will try to just look at traditional or analytical techniques, what techniques we've been using for the last so many years, up to about 10 years ago, when of course learning techniques, more specifically deep learning techniques, started taking place. And I'll try to see, I don't have solid answers, but nevertheless entertain some questions that I'll talk about as to, if you're given a choice, so should you use a well-established analytical technique to solve an inverse problem, or should you go 100% into deep learning, or better yet, is there room to combine the two? And that's one of the messages that I want to pass along, that indeed I believe in very many cases the benefits are increased when you combine model-based or analytical techniques and data-driven, such as deep learning techniques. So these are the objectives I just mentioned, to do some comparison. We have a review paper that just came out last year that is just addressing some of these questions a little bit more specifically than I'm going to do here. But some of the questions to be addressed are, again, what are the relative advantages of analytical and learning approaches, and put it differently, if you have again a specific problem, which ones should you use from the toolbox that you have available. And under what circumstances one approach should give you better results than the other. So I don't have solid answers because there are no solid answers, but we will draw some conclusions at the end of the presentation. So an inverse problem is one, to say the obvious, you have a system that an image or a video or two-dimensional data go in, that's what you observe. Again, it could be an image you recognize or an image that doesn't represent the scene if you use a coded aperture or something like that, but nevertheless, from your observation, you want to go back and reconstruct as accurately as possible the data you would like to capture. And depending on what you know and you don't know, you can have a system identification, implementation problem, but inverse is a problem when you try to go from the output to the input, clearly. If you don't know the system, it's a blind recovery. If you partially know it, it's semi-blind. But again, the question here is what should the tools be to carry out this inversion that we are interested in? For the parameters to be estimated. Okay, if we just do some high-level comparison with analytical techniques, it's part of the equation, if you wish, that you have to incorporate domain knowledge into the reconstruction and inversion system. While with learning techniques, this is a harder thing to do. And we'll see some ways to incorporate prior knowledge by using, for example, GANs, or by appropriately choosing the cost function that we are going to end up optimizing. One of the big advantages, of course, of learning techniques such as deep networks in particular is that we have a fast inference. It might take you weeks or months to train a network, but at test time, it's typically a feed-forward pass that you don't even need a GPU or anything very powerful. It's very fast, while on the other hand, with most analytical techniques, you end up iterating, and that takes time. And of course, with analytical techniques, since you've done this strong modeling, you only need one observation. Given your observation and your model, you can go back and solve the inverse problem. While on the other hand, in learning, you require a large amount of data. And this is an important point because clearly there are tons of data on the internet and many other applications. However, there are applications which are data starved. You don't have enough data. Or the data you require, and I'll try to make a point along the way, are kind of specific data with specific degradations that are generated by your analytical system. So that's an important point. Okay, so I'd like to go real quick through a problem that we follow a standard, traditional Bayesian type of approach in solving, but I will make a point which I will revisit at the end where deep learning can take a place. So uncalibrated tomography means that you solve the tomography problem, but when you do nanotomography, for example, the specimen here, the 3D object, is subject to shifts, three-dimensional shifts, X, Y, Z. And of course, if, you get the projections as shown here, but this is the case where this is the standard fund of this is the sinogram, so you have angles on the horizontal axis and the projection on the vertical axis. So if the specimen is aligned, we have a nice sinogram, we have a nice reconstruction using your favorite approach. However, if there's this shift that I'm talking about, right, then the sinogram looks like this, and using the back projection or whatever, we have a lousy reconstruction, right? So again, this is a real problem in a good number of applications. We work with people at Harvard National Lab in Chicago. They have the advanced photon source there. They acquired a lot of data with X-rays that try to go down to the 10 nanometer resolution. This is again the same pictorial. We have this shift, and of course, the shift is three-dimensional, but you see here the Z and the planar one that you can capture on the component of it. So what you do with analytical techniques, you build a forward model. So the three-dimensional object F, this is the rate of transform. So you take the object and you raster scanning, you turn it into a vector. So this is a matrix of the, just, you know, the integral, which there's no need to go into the details how you exactly write this matrix. And then this is the matrix that expresses the lateral shifts, right? So given y of I, the ith projection, and you have capital S of those, you try at the same time to estimate, excuse me, f and t of I, right? A standard inverse problem. So we use ADMM to formulate it. So we introduce a new variable p of I that we want to be equal to the observation, the data. You model the observation as a Gaussian. This is the Lagrange multiplier that we need to model. This should be 0, so the u should be close to 0. This is the TV prior on the 3D object. And here there are the non-informative priors of the shifts and the other parameters that we need. So this is where all your domain knowledge goes into. That's the power of your prior knowledge. And then with one observation, you try to minimize this function out, and using, again, ADMM, you have 5 iterations that you need to update. Okay? And in one iteration, you solve the denoising problem. Don't worry about all the math, it's after lunch. I'll be glad to walk you through one by one, but the main message is you have a denoising problem, you have a reconstruction problem, you have the alignment problem, you solve for t, you hyperparameters and update q, right? And these are steps that are dictated by ADMM. So this is, again, the fully analytical approach, but as we'll see also, some of these problems, such for example this denoising problem, is something that can be solved effectively using a neural network. Because this is the noise, this is not the white Gaussian noise, this is the noise that is generated by your analytical technique, this one that gives you an estimate of the object, right? So this is, you denoise with a type of noise that you cannot express adequately. This is not your white Gaussian type of noise, but these are the artifacts that are generated by your analytical technique. So ADMM, by and large, and I'll revisit that at the end, is one of the approaches that allows you to take an inverse problem and separate it into 2 problems, a denoising problem and an inversion problem, like single inverse filtering, and then denoising. And the denoising, you see benefits doing it through deep learning because, again, this is a type of noise that you cannot adequately characterize with the prior probability density function, right? On the other hand, the inversion problem, you know, you have y equals ax, and there is a square invertible matrix, and it's clean of noise. There's absolutely no need to go to a neural net, right? I can invert it numerically very successfully. Okay, so for this problem, here is the observations, and we compare with another method we developed with colleagues at Argonne. So this is the results, this is the sinogram, and this is what you get with this Bayesian method, and this is the object that gave rise to these sinograms. So these are the 2 methods, and as expected, you might say, when the misalignment increases, you get improved results with this Bayesian approach. And these are the shifts, horizontal, vertical shifts, different amounts of noise, and as the noise increases, clearly you cannot do as good of a job in estimating the shifts. The vertical one is easier to estimate for a number of reasons, but nevertheless, it's a very satisfactory job. Okay, so purely analytical technique, but yet it invites the combination of analytical and learning approaches. Compressive video, talked about it yesterday and today. We did a lot of work on that. So I had it in my presentation, so I'll say a few things here. Oops, pressing the wrong button. Okay, so this is temporally compressive, right? You acquire one frame and you try to extract X frames, 10, 15, 20 frames, right? We increase the frame rate by a specific factor. So it's very similar to the spatial compressive sampling. We build a system at Northwestern with professor, my colleague, and some other visitors. So we have a mask which you have a translation stage, it translates while the aperture is open, that's the system, and we can acquire data. We have also replaced this more elaborate system with a specific sensor that we can program at will and implement the different masks. So mathematically, again, what we do during exposure, you change the mask. So in essence, what you observe one image, which is the product of the mask with the frame, and you sum it up together, right? So knowing the masks and this observation, you try to recover a video, right? So from one image, you try to recover 16, 20 images, whatever the factor is. Okay, so one measurement, you try to reconstruct what's on the right. We looked at analytical techniques as well, but what I'm talking about is just a network. So we put together a fully connected network for this. It seemed to do the better results. Actually, in the cost function, we also need the residuals because we have a regularizer here, which is in the gradient domain, and here you see the residuals that we simulated. That's the network is a fully connected network. You train it, and here's some. Oops. This is a result that compares with David's and Sin's approach and what we did. Okay, this thing is acting up a bit. So what you see the original at the bottom, and then the Gaussian mixture model, the analytical approach here, and what we obtained with this network. Right? And I think by and large, depending where you're sitting, you see a bit more, a bit of improved, I guess, result coming to this. But of course, the inference, you spend time training, but the inference time, this is kind of very fast. And you see a similar thing here. You see some artifacts here that are not as many on this one. We do it a step further, which is instead of using random masks, as it's typically done in practice, in the community, we also ask the question, okay, are there certain masks that are more suitable coded masks to improve performance? So we have an encoder decoder here. So here you solve for the masks, and then based on which you utilize to compress the sequence into one measurement, and here's the other network that we already showed that will do the reconstruction. So this is the training part, this is the testing, but anyway, it's an encoder decoder architecture. So it's an autoencoder in essence. The input you can find the input at the output. And we put this to work, compared it with different approaches, and here is the average PSNR at different levels of mass. So here you only have 20% of ones, so it's a 0, 1, the mask is a binary mask, and here you have 40% and 60 and 80%. Interestingly enough, the masks we end up designing, they look like this, not as random as the random mask. They seem to have some structure. So it's a 4x4, so vertically 16 pixels, and the horizontal axis is time, right? So I don't know how many time instances here, but the number of masks, of course, determines the compression ratio, right? And again, here is a. So what we show here, we show with the dictionary technique what happens if you use a design mask by the network and a random mask. So using the designed mask, you get better results than the random mask. And the next one, is where we compare the dictionary, the Gaussian mixture models, the TV-based, and then the neural network reconstruction. But they all use the design mask, so the best possible performance. So now it's the power of the reconstruction, and you can also see, yeah, some of them are synchronized, some are not. It's not necessarily so easy to look at this, to get the results rather, but we have some PSNR metrics here as well. Okay, so this one was done here using neural nets. Here is a project we have actually with Aggelos funded by DARPA, whereby we combine deep learning and analytical techniques, not for solving exactly the same problem, but solving parts of the problem. So the idea is to, actually at some level relates to what David was covering yesterday, but you have, for example, a high resolution focal plane array, and you want to have a structure, we call it flexible asynchronous space-time imaging, but in some sense it's going to tessellate the three-dimensional space, two spatial and one temporal dimension, by taking each and every frame and then paying attention to areas of interest, so sampling efficiently certain parts, both spatially and temporally, right? So building volumes like this. So we envision, so this project has other people building sensors and so on. Reimagine is the project, and the way we're looking at the problem is to have the sensor with its own capabilities, but yet offload some of the capabilities to the computer, which would be right next to it, or would be kilometers away. And of course, an interesting question is how you balance the computational demands between the sensor and the host that in principle can be a very powerful host. So for this to make sense, there's some prediction from here where to look, and then it requires data, and there's some correction here, so it's a prediction correction mechanism. But nevertheless, to pose the problem as constrained by the pipe that connects the sensor to the computer, right? And this pipe, it's kind of a similar argument that David made yesterday, that, you can say that pipe is whatever it is, and of course, as the capabilities of this increase, this is going to be a constraining factor. So you can always do better if you consider what the limit is here by considering the most powerful sensor. So on the chip, the type of thing we are doing, we do a quadtree-based compression. Like we solve an optimization problem that is going to tell us how to tessellate a frame here with varying sizes blocks is shown here. For some of these blocks we acquire it, for some of them we don't. So you only acquire the blue blocks, and then you send to the host your acquisitions. So in each frame you want to tessellate it like this. Also, if you want to encode, there is a Hilbert scan that underlies this, that tells us how to visit the different blocks. And there's a parameter there, a lambda, that multiplies the rate. So the larger the lambda, the smaller the rate. So if you compare this tessellation of this frame and this tessellation of the same frame, this provides more accuracy. If you go down to smaller size, because we have a more higher rate that you can communicate between the camera and the computer, right? But then the host can do whatever things we want it to do. One of the things is to do object detection. So detects objects, and based on the classes, it does classification, ignores some of them, and gives high priority to some of them. And then using a Kalman filter type of structure, it can predict the location of the bounding boxes of the objects of interest. So this is an example that you just have a bounding boxes based on the detection. So you see a distorted video here to do compression, and you saw how it did in detecting and tracking these objects. And this is, of course, a false positive. It's not a car. It's a similar thing with this plane sequence that it does a good job for the better part. Now, one of the issues here is how you do the object detection, and we use a neural network to do so. But in training the neural network, if you use pristine quality data to train, to do object detection, you get a performance like this. So what we have here is this is a metric for measuring tracking accuracy. So it's a kind of end-to-end objective. If tracking is the objective, the object you detect how well you track them. So, and here is the distortion. The distortion of the video increases here. So if you train the object detector with pristine data and test it with distorted data, then the performance of the object detector is going to drop considerably, right? So you need to train the object detector with data similar to what is going to encounter in practice, right? So you have to train with data that are degraded the same way that this particular system is going to degrade them at the level of degradation that is going to encounter in practice, right? So this is an example where having adequate data of the right type to train the neural net is very critical, right? It's easy to find examples from the internet and train, but you have to have the degradation that the data is subject to based on the system. Okay, and in case where it's trained with degraded data, it maintains some better performance. Now, in addition, we can do edge reconstruction on the host, right? If the host is the more powerful one, you can just put additional advantages or requests and so on. And the edge reconstruction, we use a neural network like this. Here's the loss. I couldn't spend time explaining the details. So this is what you observe. This is the pristine data, and this is to do. This an important part. Anyway, to do the edge reconstruction, we use also events. We use a DVS to give us the events, right? The asynchronous events at a much higher rate. So using the events and this observation, we can reconstruct, we can bring this quality to this quality, and then we apply the object detector to this, which is doing a better job, better performance. So this is the degraded, this is the pristine, this is the reconstructed, utilizing this observation as well as event information. Now, another direction we took it, utilizing events, is to assume that the events are available on the chip, right? And then we do event filtering. I'll say a few things about it. Then we can use the events to do object detection and fuse the information, the detection results on the chip with the prediction that is provided by the host. So we have a fusion here of the observed frames and the predicted bounding boxes, that is, and then is the information that is utilized for the optimization and that is sent back to the encoder. So we utilize another neural network, Aggelos, and this is event information based on which we're able to classify, detect and classify an airplane with high probability or a car with high probability. Now the other thing we do with events, we have quite some work with events that I'm going to talk about here. One is to have one frame and events and reconstruct the video intensities at higher frame rate. Here we use event information and one image to filter the events, to sharpen them up. So there's motion compensation involved, so the guidance is provided by the high-res image, and the filtering means that instead of getting something like this, you get edges that, so you aggregate event information here, and after filtering it looks like this. So the edges, if you wish, the temporal edges are thinner and sharper without this. And down here is some technology. We do this with RGB and the inventor RGB. So again, this is the aggregated events, and these are the events after filtering. So you can see that again, these are thinner and sharper. These temporal boundaries. And here we show the input and the output for the RGB planes since we do color processing. Okay, then I want to talk about another topic, that of video super resolution, and try to come back again and make the point of how to possibly combine learning and analytical techniques. So this is the system. You have you observe video frames at some given resolution. You have a number of effects that take place, and the idea is you operate on this video sequence and you try to increase the resolution. And no matter what the resolution of your camera is, you can always go to improve even the state-of-the-art camera, the same argument that David made yesterday. This is geometric super resolution, so if it's a still image, what you observe is 4 raw resolution images, and you reconstruct this. And what does the trick here is that you assume that there is subpixel shifts between the images, right? And we have plenty of Bayesian type of approaches in solving this problem, and you find the shifts at the same time. The shifts are not linear shifts. You can assume more complicated affine models and so on. So what we do here in some of the recent work, we use this generative adversarial networks, and these GANs allow you to bring prior knowledge into the problem, into the learning problem, right? So allow you, without modeling explicitly the type of images you want to represent, by sampling them to incorporate the prior into the problem. So you solve a min-max problem. So I don't know if you're familiar with GANs, but there's a generator and a discriminator. So the generator has as input low-res frames, as output high-res frames, and then the high-res frames are shown to the discriminator, and the generator is trying to do the best possible job so as to fool the discriminator to believe that what it generated belongs to the same class of images that the discriminator has access to. So the discriminator has actual examples of high resolution images. So it's like the generator generates counterfeit currency, and the discriminator is the police, and you say, is this fake or real, right? And the discriminator wants to improve the performance of the generator by pushing the generator to generate something that would look as if it was drawn from the set of real currency. So you solve this min-max problem. So d of x is 1 if it's a true, it comes from the true distribution. So x is the true distribution, y is the low-res data, x is the high-res data. So when you train the generator, you minimize this expression, and therefore you minimize only this, right? And the minimum here is when this is 1, so the log of 0 is minus infinity. And this is 1 if the generator that has as an input a low-res image generates an image that the discriminator is going to say, oh, that's a real image, so this is going to be 1, so 1 minus 1 is 0. When you train the discriminator, you try to maximize that. It's a min-max problem. So this is 1, right? So this is 0, and then the discriminator is going to say that this is fake. It's going to be 0, so this is going to be 1, so the maximum of this expression is equal to 0. So anyway, you train these two guys. This is a particular network we use. We use residual plots and so on. This is a paper just appeared this year. If you take 5 frames or 7 frames as an input, you find one output. We did a number of things along the way, and that's also part of the direction of bringing in knowledge into the problem. So, for example, try to compare the output of your system to the original image, not in the pixel domain, but in some feature domain, which eventually also expresses property of the visual system. So you take the low-res image and you map it. So this is the generator. And then you compare the output of the generator with the original data when you train. So you have this loss in the pixel domain. But also you take this and you map it, let's say you use a VTG16, whatever, and you take one of the layers, the 10th layer, doesn't matter, a feature space. So you have a feature representation of this data and the feature representation of the true image at the same layer. So this is the loss at the feature space. So you change, so one of the messages here is that what makes one network more effective than another is what do you train it on? What is the loss function that you use to train the network? And it's not just the mean squared error, you can have multiple terms. And that's one of the ways to bring prior knowledge into the problem, right? So you can use, for example, spatial adaptivity. We know from image recovery that treating the image in a spatially adaptive way so that not all pixels are equal, but some are more important than others, such as edges, that can help. And here is an example of a loss based on which we train the discriminator. So we have this feature loss that I mentioned, and gamma is the Charbonnier loss, it's not exactly mean squared error. Then this is the GAN loss that I went over. This is, again, when you train, so this is when you train the generator, and then you have the pixel loss based on this view as well. Here are some results. It doesn't do justice to 4K images, and you have to build them up and see it on the big screen, but nevertheless, this is with the feature loss, this is without the feature loss, and then you zoom in. Hopefully you see more detail here than over here, more detail here than over here. This was a factor of 4 in what we mentioned at the outside. Okay, now here's an important part that, that I want to point to, kind of whereby tying analytical techniques with one-way time analytical techniques with learning can give us benefits. So it's again the super-res problem. I observe Y. This is my low-res video. X is the high-res video, which is blurred by AK and then downsampled. And I can learn the input-output mapping as I've been doing all along. But if we look at this expression, don't worry how it came about. We see here that there's a network f of theta that I'm going to train upon, and using these equations, I can find the g of theta. Now, this g of theta is the high-res image that I'm after. If I pass it through the system, A is I group together, A is the forward model. If I pass this through my system, it's going to give me the low-res observation based on properties of the generalized inverse. So, the moral of the story here is that I don't need to learn the overall end-to-end mapping, but I can learn this residual mapping, this f of theta, if you write it, is really the residual. So I learn the residual and then use analytical knowledge of the operator A to come up with the end result. And this has two benefits. It makes learning easier, faster, more efficient, but also it allows me to address the mismatch between these operators. You know, what typically happens is this forward model took place in Japan, not that they have anything with Japan, with the system that was developed there, and then I tried to do super-res in Chicago, right? And I don't know what this A is that was utilized in Japan, right? But through this system, because I learned the residuals, I can assume an A in Chicago, and I learned this difference here, so I can carry out the super-res with different models. So that's what we modified the previous architecture, and I used a neural net to really find the generalized inverse, which is input to the system. And by and large, this is the high-res, so that was, you know, different versions of the network where a different A was used in the forward and in in the inversion model. So there is a mismatch between the models, and as expected, you see something blurry. But utilizing this network, this affine GAN, as we try to, you see that we can do a much better job. It's not the original, but nevertheless, it's considerably improved than what we get otherwise. And of course, you can think of this as end-to-end mapping as well. How am I doing time-wise? So how much more time? 10? Okay. So, yeah, the idea here is I can take the signals, I map them in a feature space, and then I can do the mapping in this feature space, so I can further, it's a twist to the whole thing of reading in prior knowledge. Okay, so the marriage of Figaro here. Different ways to combine analytical and learning techniques. And one of them was through GANs that I showed about. I don't know if it's registered to everybody, but the use of the adversarial network allows me to bring in prior information about the distribution of the images that I try to super resolve in this case or invert in general. And the second way was through this affine GAN, whereby I impose constraints of the solution. The constraints are that they have to satisfy the forward model, which allows me to only learn the residual. So I constrain the space, the solution space, and this makes the whole network more easier to train and more effective. Deep unfolding, so these are just suggesting ideas, is another idea that I can use all these words. There was a paper in 2014, and then we'll be doing some work, but also other people picked up on this. So the idea is take your favorite analytical algorithm that is typically, again, assuming it has some sophistication, we end up with optimization solutions, right? Iterative approaches. So the idea of unfolding is I can take an iterative algorithm and write down 2, 3, 4 iterations, and that's my network, right? So I use an analytical technique that brings in all the prior knowledge, and I unfolded the iterations, and this gives structure to a specific network that I can now train, right? Your solution is as good as the number of folds you did, but nevertheless, it shows to be quite powerful because, again, you can directly incorporate the prior knowledge. So, yeah, we can apply it to some of the problems we're looking at and also apply it to some medical applications and so on. So this is another way, again, to combine analytical and learning techniques. The other way is what I already mentioned, write the equation. So you want to solve y equals ax, and the approach of alternating directions of multiple multipliers, or is it alternating directions of multiple multipliers? Okay, so you have y equals ax, you introduce a new variable z, x equals z, and you write the problem like this. This is the original problem. You put, instead of x, you put z. This is the constraint. And then following the steps, you form the blended Lagrangian. That's what I did when I talked about the tomographic problem. And right, so, when x equals z, this is x equals z, this minimum is zeros, this kind of drops out, and we have the standard regularized least squares problem. But the iterative procedure, kind of resulting from ADMM, allows you to solve two problems. You solve for x, you solve for z, so the introduction of the second variable z allows you to decouple the noise filtering through the inversion problem, right? So here I solve for my x, and what you see here, it's x plus something plus a regularizer. So this is a noise smoothing problem, right? And this noise smoothing problem can be efficiently solved with a neural net or a learning method, simply because this kind of noise here is not your standard Gaussian noise, but it's the noise that is generated by solving this problem. So this problem solves for the unknown, but it's a quadratic now, right? It's quadratic in Z, quadratic in Z. So I can have a closed form expression for that, right? So by using ADMM, I can again solve an easy quadratic problem through inversion, and then I have a problem that I can use learning. Some people refer to this as plug and play approach, in the sense that I can use anything here, right? The word of caution is that when you train this neural net, if you train it with white Gaussian noise, it will not be the best one. So this is another example where you do benefit, for those of us that tried it, quite a few people tried this, you have an easier problem to solve through learning and a piece of cake problem to solve through inversion. And variable splitting is doing exactly the same thing. You solve y plus hx, I change that matter, but nevertheless you introduce another variable. So you have a denoising problem and a fidelity sum problem, just having the same problem. Here's another way of thinking. You have the set of natural images. Let's say you solve the classification problem, so you find a classifier that will do a good job with natural images. So this is d of x, and then you project this proximal operator of d of x onto the problem you were trying to solve. It would be this problem, this problem, this problem. So you do this proximal projection into one of these planes, and this way you can solve with, you solve the problem once and through this proximal operator, you can bring the prior knowledge about the natural set of images that are underlying your observations. So the final thoughts, if I have more time, I can say two more things, but I'm going to finish with that. So learning through deep neural networks, although not precisely understood, provides fair competition to modeling techniques, capitalizing of course on the power of GPUs and the abundance of data. But the impressive achievements that we have seen in the cognition type of tasks, where human performance has been exceeded, right? And they do not necessarily transfer directly when I solve inverse problems, which is a regression problem, right? We do see good results, but it's not on one hand the quantum jump that we've seen in some of the classification type of problems, and two, the result we've seen could potentially be improved by using some of the ideas that I mentioned here, and of course additional simple ideas. And by and large, to state the obvious, that the use of neural networks is advantageous when you have kind of complicated problems for which you don't have good handling of modeling. You don't have a precise way to model, the system, what is happening, the forward model. And then you have to make sure, of course, you have the right data, because very often we train neural networks with simulated data. Like this low-res, high-res problem that I talked about, that we've been working on. We simulate the low-res and the high-res acquisitions. What we would like to do is to have examples of actual systems that provide you both type of data and so on, and therefore you can learn about the system. So training, again, a neural net with simulated data may not give you the best possible results, but if you don't have a good handle of how input-output are related, then there's more room for that. So, in addition, kind of going a little bit deeper, we try to look at that most of the current TL approaches can be thought as maximum likelihood or map methods, not necessarily fully Bayesian methods, and also analytical techniques can benefit from capturing more modular certainty and using approximate inference with methods like variational Bayesian and expectation propagation, and GANs and variational autoencoders. That's an idea where we approximate the posterior of a variational Bayesian, and this gives rise to the autoencoder. Can be used to have a better understanding of the neural nets. There's the result here where the dropout can be thought of as a variation of Bayesian approximation. But by and large, for most of us, it's kind of the black box, the neural network. We don't fully understand what's going on. We try it through visualization, through other techniques to have a better handle, but they lack interpretability also. We don't know what these features are all about, which could be fine in some applications, but some other, for example, with medical images, for the MD is very critical to know what are the features that the system based its decision on. So, this is it, and then what I talked about, there are a lot of people behind it, Rafa Molina, my collaborator, Roddy Cosser, Mark Balton, some postdocs, and some student graduates, and some students that are still there. I had a few words on dictionaries, but I'm okay, I'm over it, or? Anyway, all I had a couple of slides was that there's dictionary learning preceded, well, in some sense, deep learning. It's learning all right, but yet the reconstruction is rather tedious, right? You need to do optimization, unless it's a VQ. And VQ used back in 2003 kind of ideas of dictionaries to solve restoration problems. But also we used VQ, not VQ, dictionary learning to solve the bigger super resolution problem, and you minimize things like that. The main idea here is that we have coupled dictionaries. You have a spatial representation of the low-res data, coupled representation. Okay, we have a spatial representation of the low-res data, a spatial representation of the high-res data, but the representation coefficients are the same. So you have two different dictionaries, but it's the same atoms in the low-res dictionary. The same atoms in the low-res and in the high-res, the same location of the atoms that will express the low and high resolution picture. So this is the idea of the coupled dictionary. Anyway, I won't cover with all the cost functions. So when you observe the low-res image, you find the sparse representation, and you use the same representation coefficients, sparse coefficients, to go to the high-res dictionary and to construct the high-res dictionary. But anyway, there are a lot of things that can be said more about when they compare and so on. We're also doing work in the cultural heritage domain. This should be, so this is an XRF scanner, and this is the bedroom by Van Gogh at the Art Institute. So we do different things, smart sampling. If we have a point-wise sampling of a painting, it might take you a day or two to cover the whole thing. So we're looking at adaptive sampling. We're looking also at combination of XRF and RGB images. So we have an XRF volume, like 4,000 channels of low resolution. Yeah, this was supposed to look differently. But, and you have a high resolution RGB, and through dictionary learning you can increase the resolution of the high-res XRF. For the sampling, we learn a mask. So the idea is that given an image, a painting, you want to sample the most informative samples, and ties to active learning actually, if classification is the problem. And you can do it at random, but you can do better if you find which are the most informative pixels, and then you solve an in-painting problem. And you can learn this through a neural network, the most informative pixels, and then we have another network to do the in-painting. And this is how it looks. The resolution is the same. So this is the XRF, and this is the RGB image. So this network tells me how to sample this, and then we have this Gandry that can control and can go and visit all these locations with the adaptive sampling, and then we do reconstruction up here. Okay, this was it. I'll